Hello, my name is Malik, and I'm here to present to you our recent work on lifting uniform distribution learners via distribution decomposition. This is joint work with some wonderful people, Blanc from Stanford, Jane Lange from MIT, and Professor Liang Tan, also from Stanford. So the outline of today's talk is as follows. Firstly, we're going to spend a bit of time talking about the background and motivation behind this work. Then we're going to dive into some of our approaches on decomposing distributions and using these decompositions to lift uniform learning algorithms. And lastly, we'll end on some closing remarks and some future directions for our work. Okay, so let's get started with the background and motivation. Let's begin by going over the standard framework used in learning theory. In this setup, we're given a few objects. Firstly, we have some distribution D over our domain. In this case, the domain is the Boolean hypercube. On top of this, there's also some function f. This function maps points in our domain to something like 0 or 1 in the classification setting. Now, this function is completely unknown to us, but it is also the function we're trying to learn. And the way we get to learn this function is by observing some samples. So we get to see some IID samples from our distribution that then get labeled by this function. And our goal as algorithm designers is to design efficient algorithms that take these samples and output some hypothesis H that also maps points in our domain to 0 or 1. And what we want is that H should be quite similar to F. In other words, we want the probability that F and H disagree on a point to be quite small. Now, looking at this setup, with a little thought, you can convince yourself that there is no way to design efficient learning algorithms without making any assumptions about the function f or the distribution d. So what happens in learning theory research is that we often make some assumptions. And some of the most common assumptions involve assuming something about the function f that we're trying to learn. Some examples of this are as follows. We might assume f belongs to a function class with low VC dimension, or that f has some structural property, for example, low decision tree depth or low polynomial degree. Now, when we make assumptions about the complexity of f, we are allowed to design algorithms whose efficiency scales with respect to this complexity. Now, this has led to rich connections in the study of function complexity and learning theory. However, the focus of this talk is not about the complexity of f at all, but rather about the distribution D. Now, to answer this question, we have to think about how the distribution is usually treated in the learning theory literature. So on the one hand, we have what I'm calling traditional pack learning or distribution-free learning. In this setting, we make absolutely no assumptions about the distribution D. This is an extremely strong setting, and it has this wonderful pro that if you can achieve this pack learning guarantee, you can rest easy knowing your algorithm will work no matter what the distribution D is. The flip side, of course, is this is an extremely difficult result to achieve. There are fairly simple function classes for which we don't have results on efficiently learning with respect to the distribution-free setting. And on the completely other end of the spectrum, we have distribution-specific learning, where we assume D is some nice distribution. This nice distribution is often always something like uniform or Gaussian. And in this setting, what we get is access to these incredibly powerful techniques and hence the ability to design faster and more efficient algorithms, because D is known to be nice. However, the flip side of this is that this is an extremely unrealistic assumption. To really emphasize this point of the sort of extremes that these two distributional assumptions provide, here are some fairly simple function classes and the efficiency of different algorithms in the traditional pack setting and the uniform distribution setting. So for DNFs and intersections of two half spaces, we see there's an incredibly large gap between these two settings. If we draw a spectrum of the distributional assumptions you can make, it's quite clear that on one end is the traditional pack learning setting, and on the other end of the spectrum is the uniform distribution setting. The purpose of today's talk and our work is to understand what can be done in this middle region between these two extremes. In particular, we want to answer the following key question. Can we interpolate between these two extreme assumptions via some notion of distributional complexity? In particular, can you design algorithms that automatically scale with the complexity of your distribution? This is the question we're going to be answering in our work. Now, there are many ways to tackle the problem of, for example, defining distributional complexity. In this work, we present just one approach, and that is using this idea of distribution decomposition. Now, what do we mean by that? This idea starts from a fairly simple insight, which is that we already have these incredibly efficient algorithms for learning with respect to the uniform distribution. Now, here's a question. Can we extend these algorithms to distributions that aren't uniform, but are pretty close? They're uniform-ish. Now, what do we mean by that? We want some intuitive measure of complexity that sort of measures this idea of being uniform but not quite. So here I've drawn our domain as a square, and you can see we have one mass uniformly over this entire square. This is the uniform distribution setting. How about if you're not uniform, but perhaps you're uniform over the left half of the domain with total mass 0.3, and uniform over the right half of the domain with total mass 0.7. One could say this is not a uniform distribution, but not too far away from a uniform distribution. And as you go further and further in complexity, perhaps you start getting these distributions that are uniform over quite a few different spaces. And this is some intuitive notion of complexity. A key point here is that your distribution is partitioned up in some way, where you're uniform when restricted to each partition. And each partition has a weight that it contributes to the total distribution. Now, the way we actually instantiate this in our work is through this idea of decision tree distributions. Now, decision tree distribution is simply a distribution whose probability mass function is computed by a depth D decision tree. So to figure out the probability mass on a point, you might follow the queries of a decision tree until you hit a leaf. And then at that leaf, your distribution is uniform over all the remaining points with total mass given by the value of the leaf. Some important things to note here. Decision tree distributions form the subcube partitions of your space. So they capture this idea, this intuitive idea from the last slide. Moreover, the distribution at each leaf is uniform, right? And lastly, that in this setting, the depth of your decision tree is a natural measure of how complex this distribution is, right? If you have depth 0, then you're uniform. And if you have depth 1, you're uniform over 2 parts of the Boolean hypercube. Okay, so what do we do with this idea of decomposing distributions? Well, our goal is to take uniform learning algorithms and sort of lift them so they work on distributions that aren't completely uniform. And the high-level idea here is as follows. Let's say we have our domain again, the Boolean hypercube, represented as a square. Your first step is to decompose your distribution into uniform parts. Now we'll talk in a second how to actually do this, but let's say you can decompose your distribution into uniform parts. Then what we can do is take any uniform learning algorithm and run it on each partition, because each partition is uniform. And what we can do is like store the hypothesis learned at each partition. And lastly, we can combine these hypotheses to get a learning algorithm that works on this distribution tree distribution. And how we do that is whenever we want to classify a new unseen point, we figure out which partition it belongs to, and then we use the learned hypothesis at that partition. And note how this high-level idea automatically scales your learning algorithm with respect to the complexity of the distribution. In particular, step 2, if you have very few partitions, then your runtime and sample complexity won't be as high as if you had 2 to the 8 partitions. Okay, and this is great. A wonderful idea, but I haven't quite talked about how we actually do step 1. And this is the question I want to discuss next. How do we actually go and learn a decision tree distribution? Now, the fortunate thing is that we have a huge body of work, tons of existing research on how to learn decision trees. So this is great. However, the problem is, unlike the usual decision tree learning setting, we don't actually get to observe the label d of x. Right? We're trying to learn this probability mass function that is computed by a decision tree, but we don't ever get to observe d of x. So there's a little work needed to make this work. And one of our results is that you can, in fact, learn a depth d decision tree distribution. You can learn this to epsilon close in total variation distance. And there are 2 sort of cases. If your distribution is known to be monotone, you can do this just using random samples from the distribution. And in the more general setting, you might need subcube conditional samples to learn this decision tree distribution. Now, combining all these ideas, we get the main theorem of our result, which is that you can take any m-sample uniform distribution learner, of which there are many, and lift them to work on a depth d decision tree distribution with sample and runtime complexity poly n dm over epsilon to the d. Okay, so to finish off, I want to recap some of the things we talked about. The key focus of our work and of this talk has been understanding distribution complexity in the context of learning algorithms, right? We're interested in understanding how, as your distribution gets more complex, how your learning algorithms might adapt. In particular, we talked about just one approach to this problem, and it was this 2-stage approach of decomposing distributions and then running the learners on the decomposed parts. This 2-stage process of simplifying your distribution and then learning on the simplified distributions, quite interestingly is reminiscent of semi-supervised learning, right? Where step 1 just requires samples from the distribution. You don't actually need any labels, f of x. And then you learn on this like simplified distribution. So I suppose we'll end on talking about sort of the goals for the future. The goal for the future is to study further this idea of like the complexity of distributions and learning the distribution with an eye towards making function learning easier. So can we connect the wealth of literature on learning distributions and use it to make function learning easier? Thank you very much for your time in this talk. If you have any questions, please feel free to email me. My email is malikali@stanford.edu.